All right, what do we got? This was number 10 in our homework. I'm going to find the volume generated by revolving the curve y equals cosine of 4x about the x-axis. So before I whip this out in Desmos, I just want to remind myself of some basic trig. Period of a function like this would be 2 pi divided by that multiple on the inside. So 2 goes into 4 twice, so the period is pi over 2. So graph of this, cosine starts at 1 and then drops down and completes 1 period to here. That would be pi over 2 to there. Halfway, this bottom right there should happen at pi over 4. And then this root right there should be halfway again, which should be pi over 8. So I'm pretty sure that this section right here is what I'm revolving. And we'll double check that in Desmos. And I'm going to revolve that about the x-axis. Let's see, so we could either use disks or shells for this. If I use disks, then I'm going to have a little rectangle perpendicular to the axis of rotation, which involves a dx, which is nice. If I use shells, then it'll be parallel, which means I'll have a dy and have to use the arc cosine. I think cosine sounds easier than arc cosine here. So I'm pretty sure I'm going to use shells or washers for this. Or discs, sorry. Disc slash washer. And this isn't going to be a washer because there's no empty spots. We'll just call it discs. I've double checked that I got that graph right. Desmos. So we'll call this f of x, bless you, equals cosine of 4x. And we want to go over to x equals pi over 8. So zooming in, that looks pretty much like what I was aiming for there, this chunk right here. Okay. So again, when we rotate that, we're going to get a shape that looks kind of like this here. Won't be pointy there, it'll be pretty smooth. So we're going to make a dish, basically. And to get this rotational chunk of volume here, just reminder, a little chunk of this volume is going to be a disk. So my little chunk of volume is going to be the area of this times the height of it there. So the area is just pi times the radius squared times my delta x, which is the thickness. And my radius is, in this case, just a function value, right? My y. Yeah. So I'm going to have pi times cosine squared of 4x delta x is my little chunk. So putting that into an integral, my volume should be the integral from 0 to pi over 8 of pi times the cosine squared of 4x dx. To deal with a cosine squared before, we used a version of the half angle or double angle formula, depending on your perspective. And so that would be the cosine of 2, let's see, get that back. The cosine squared of theta is equal to 1 plus the cosine of 2 theta over 2. Is usually the way I write it. There's a few variations of it. So my theta is a 4x here. So I'm going to pull my pi out. And then I have a 1/2 I can pull out also. So then I'm integrating from 0 to pi, 1 plus the cosine of 2 times 4x or 8x dx. Substitution here, really, I'm just, well, not like a use substitution, right, or integration of part substitution. I'm just using an identity here. And my identity, again, is cosine squared of something is 1 plus cosine of twice that something over 2. In this case, the theta is the 4x. And so I get 2 times 4x here. The half I pulled out front. Antiderivative of this, pi over 2 is just chilling out there. Antiderivative of 1 is just x. Antiderivative of cosine is the sine. And then since it's an antiderivative, instead of multiplying by the 8, we divide by the 8 or multiply by 1/8. And then evaluate this from 0 to pi. And again, these are kind of nice numbers. I'm just stuck with a bunch of pi's. So I'm going to evaluate this without a calculator again for fun. So evaluating this, we're going to get a pi over 2 times plugging in pi plus 1/8 sine of 8 pi. And then minus parentheses plugging in 0 there. So what happens here? Well, I like evaluating signs related to pi because that's going to be a 0. That's going to be a 0. Looks like the only thing left is the pi, and it's pi over 2 out front. So it looks like the area is pi squared over 2. How should we check? Desmos? Yeah, so I'm going to check Desmos a couple of different ways. The 2 ways I'm going to check it is I'm just going to plug my original in and do numerical integration. Then I'm going to plug in my antiderivative and see if my evaluation is correct. All right, so let's check it out. All right, so we're revolving this, right? It's not an area, it's a volume. And my numerical integral is the integral from 0 to pi of pi times the cosine squared of 4x dx. And I believe that value there is pi squared over 2. Cool. Double checking my evaluation, I believe my volume function, let's call that v of x, is equal to pi over 2 times parentheses x plus, what's that?
I have a question.
Yeah.
So why are we integrating from 0 to pi?
Oh, 0 to pi over 8. Oh, I messed up. Thank you.
Oh.
I started with a pi over 8 and then I switched to a pi. All right, so I think this still comes out pretty nice. So that should be a pi over 8 there. Pi over 8 here. And instead of a pi here, that's a pi over 8. And that's a pi over 8. Right, those are my 2 evaluations. All right, so this, again, if we were going from 0 to pi, I got that right. To go from 0 to pi over 8, the only change really, 8 divided by 8 cancels, leaving just the pi. Sine of pi is still a 0, so that does go. And instead of a pi, I have a pi over 8. So I also have a times 8 over here. So the actual area should be pi squared over 16 for that chunk. Good catch. All right, let's double check. So then here, that should be 2 pi over 8. And then this down here should be 2 times 8, or 16. Cool. And then over here, my antiderivative was x plus 1/8 sine of 8x. I don't need to see the graph of it. And then we would just evaluate that. What is v of pi over 8? Minus v of 0. And we can see v of pi over 8 is giving us the right answer. Let's pretend we didn't know that. Just double check. Also subtract the v of 0 to be sure. All right, so big things here. For most of these problems that we do, I'm hoping we can come up with an antiderivative that we can evaluate. Evaluating it by hand is fun sometimes, but not always necessary. Computer evaluation for that part is fine too.